So we're going to start learning about one of the most important tools to a chemist. It's the periodic table. It's not just a willy-nilly arrangement of elements. It's an arrangement of elements that lets us figure out a lot about the behavior of elements and about their structure. So let's talk a little bit about science again. In Unit 1, we spent a good bit of time talking about the nature of science, and we said that the goal of science, the big goal, the main thing, the big kahuna, the top banana, whatever, of science is to try and figure out the way the universe works. In fact, it's to develop defendable arguments to explain the way the universe works. Well, how is it defendable? It's because you've got evidence that's repeatable. That is to say, if you test the evidence, you get a result. If other people test that evidence, they also get the same result. Okay? And so, evidence to explain the way, evidence to support your arguments for the way the universe works. In science, a lot of times, we'd like things to be a little bit easier as far as how things behave. It'd be nicer if they fit the patterns we'd like, but it doesn't work that way. You've got to go with what the evidence is, what nature is, okay? And you're going to find that to be the case here with the periodic table. There's a lot of awfully good patterns in nature that makes the periodic table the primary tool of chemists, the number one thing that chemists use to try and figure out the way things work, because we already know these tests have been done over and over again, and we can see how that works, and so we're going to make predictions starting with position of elements where they're placed on the periodic table. But some of it's not real clean, so we got to know how to use it and when to move it around. The old song is, got to know when to hold them, when to fold them. Well, that's kind of the case here. You got to know when the pattern fits and how to sort of shift that pattern a little bit to work with what you're trying to do. So what we have here is a periodic table. We're going to start with, we have a bunch of different arrangements of the periodic table to explain these patterns, okay? And the first I want to talk about is just a naming system, okay? It's something we call the representative elements. Okay? It's not really a pattern so much as it is kind of a pattern, because the things that aren't the representative elements don't follow the pattern quite as nicely as the representative elements do. So we can find a lot of patterns in the representative elements that we kind of don't see in the other elements, okay? And so the representative elements are located in this section right here, the first two columns of the periodic table, and the last 6 columns of the periodic table. If you're one of these people that likes to color stuff, you could color code this if you wanted to. Okay. And so these are, I'll move this over a little bit. So these are the elements that demonstrate some of the clearest patterns of relative behavior. When I say relative, I mean one thing as it relates to another. Okay? You have relatives because you're related to them by blood, they call it. Okay? Well, these are relative to where they are one to another. Okay? So we can very clearly see the pattern of relationships between this element and this element because of where they are on the periodic table. Okay, and that's how it is that Mendeleev and others, Mendeleev is primarily the person given credit for arranging elements in what we now know as the periodic table. He arranged them by their chemical behavior. And that's how we started figuring out, it helped us to figure out the structure of the atom. The way that elements behave, the way that atoms behave is related to the way that they're built, particularly the electrons in the electron cloud. But the electrons in the electron cloud are there in their arrangement because of the protons in the nucleus, which are there in groups only because there are also neutrons in the nucleus. Okay? So that all those parts are necessary to understand what's going on. But for chemists, we mostly care about what's going on in the electron cloud. The electron cloud would not be structured the way it is if it weren't for everything else. But for chemists, it's the way that we move electrons around that causes these chemical bonds and chemical behavior. Okay? So that's just a simple one, all right? Now, everything else are transition elements of one kind or another. We'll talk about that in a minute. Okay? But these are the representative elements. Okay? Now then, let's go to, let's see here. While we're on the periodic table, there's a lot of things to cover. We're going to go to some other areas. Let's talk about some sublevel regions. Now, when you were in physical science, you learned to arrange the structure of the atom based on the number of electrons in a primary energy level. Okay, you may remember this. You had a nucleus here, okay, and then you had a first energy level. What y'all call that in physical science? Was it called an energy level?
A ring.
A ring, okay. It's not really a ring. They used to call it, when Niels Bohr came up with this concept, a shell. Well, the protons and neutrons are here. The electrons are in these, what we still call shells sometimes, which really is kind of a misnomer. Here's the problem. When we get down to this atomic level, nature doesn't behave the way that we're used to, you know? They don't, you know, you can't throw a ball and hit it with a bat, okay, at the electron level, all right? And so we have to start to come up with new ways of thinking about things. For example, electrons are sometimes thought of as particles, but they also sometimes behave as waves, and one does not necessarily equate with the other. In fact, one of the terms they sometimes use to describe the behavior of an electron is a wavicle, because it's not quite a particle and not quite a wave. It's a little bit of both, all right? So it has some behavior of both. But whatever you call that, it's not really a shell. It's not a ring, certainly not a ring, because it is three-dimensional, not two-dimensional. We draw it on paper like it's two-dimensional, but it's actually three-dimensional. We put electrons in here to show electrons. Now, how do y'all represent electrons? As dots? Or as E? E negative, okay. So the symbol for an electron, is E negative, okay. That's just the symbol for an electron, all right. But you might have put dots on there, and if you remember that, you said that there could be two electrons in that first ring, which really might be called a shell, which really is neither one. It's an energy level, okay. And then you could have as many as 8 electrons in the next ring, which is better called a shell, which is really neither one. It's more of an energy level, so we could put 8 electrons in here, and you could make that an E negative, which is a better way of doing it probably, because there are different kinds of dots here. I mean, how do you know this dot from that dot? So 1, 2, 3, 4, 5, 6, 7, 8. Okay, whoop, can't quite see that one. All right. And then the next level, how many electrons could you have?
16.
No, 18. Close. Yep.
Like in the nucleus, like we usually put like the protons and the neutrons, like how many
Yep.
in there.
That's what I'm talking about. Okay, so you show how many the protons and neutrons are in the nucleus. And then, so here's what happens though. Here's part of the tricky part when we get to that, okay? In this next level, you can't have 18 electrons until you have a level above it. Let me show you how that works. So here's 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay, that's as many as you can get in there until you put some electrons in this next level. Now, once I get a couple of electrons out here in this next level, then I can go back and put in 10 more electrons in here. Okay? I know that seems strange, but that's the way it works. Okay? Please don't eat in here. Okay? I know you walked in here a little late, and your neighbor right there kind of got scolded already for that. So, you know, I'm surprised she didn't help you out there and let you know in advance not to do that. But come on, help her out. Help her out. Come on.
Girl, we can't eat in here.
There you go. Thank you so much. All right. All right, so let's see how many electrons I got here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Then squeeze in here a couple of them, 17 and 18. I don't know. It doesn't really matter because they don't really exist in this even arrangement anyway. What?
I thought like an each energy level was like 2, 4, 6, or 8 or something like that. 18
No. It's 2, 8, 18, 32. Okay? And we'll talk about how that works, okay? The next level is the same way. I can get 8. Once I've filled up this level right here, then I can put 8 in here. Okay? Now, in reality, they're not really filling up quite this way, but this is the way we think about it for high school chemistry, okay? In fact, they're actually doing something even crazier than that, but we're not going to try and confuse you too much if we can help it, all right? But if we fill this level up with 8s, I say fill it up, the outer level can only have 8 electrons, and that's what we call the octet rule, okay? The octet rule, all right? Remember that word, octet rule. How many of you have played in orchestra or band? Okay, you know what a duo is, right? A duet. You know what a trio is?
Yeah.
An octet. How many is an octet? 8. Okay, 8. All right. What do you remember? The word octopus. It means 8 legs. Okay, so oct means is 8. All right. So if we fill this one up with 8, then we put 2 more electrons in a higher level, then we can go back and fill this one up with 10 more and get 18. Oh, and then guess what? We put 2 more in the next level, we can get 32 in this level. So 2, 8, 18, 32. All right, we'll get more into that as we go along. All right, but 32, although theoretically you can get more in the next level, we just don't have enough elements to get there. Okay, this is all going to inform how we do this. Now, if you're not drawing these images and following along and taking notes on this, you know, then you just got to do this when I get to it, you know, when I draw it out. Okay. All right. So let's go back here and let's talk about these sublevels, because within these energy levels right here, they don't actually exist cleanly and neatly in this sphere just anywhere they want to. Actually, these also exist within that sphere in sublevels. And so what we're doing here is arranging things on the periodic table to show how those sublevels are arranged. Okay. So energy sublevels. So if you have your periodic table, your test references out, get that out in a minute. We're going to keep going back and forth and referring to that in a minute, okay? So those concentric rings, which are better thought of as spheres, which is really neither one, they're energy levels, okay? Those represent the elements in a row on the periodic table, okay? So those first 2 electrons right here, the first electron we put in there, and the second electron we put in there, in this first ring sphere, which really isn't either one, it's an energy level. Those are the 2 electrons that we put in there for hydrogen, the first electron, and helium has a second electron. Does that make sense? Okay. And then we jump to the next primary energy level, and as long as all the electrons are in what are called the ground state, a ground energy level, which is the lowest energy level electrons can be in. Let me see if I can explain a little bit about energy levels. There's an energy state and an energy level. An electron in its lowest energy state will be in its lowest energy level. That is, it'll be as close to the nucleus as it can get. Okay? An energy state defines what energy level an electron is in, but it doesn't mean they're exactly the same thing. Okay? Think about it like this. How many of you know what a cattle prod is? You know what a cattle prod is? I see one hand up. Okay? Why don't you explain? There's 2 people with it. Okay, so y'all explain what a cattle prod is. Tell everybody what a cattle prod is. Huh? No, you don't brand people with it. Mark? You know, you don't kill them. No. Say again? It gives the cows a jolt of electricity. Okay? It just stings them. Okay? I mean, people don't want to get stung with it because we're not as big as cows, and it hurts us a lot more. But it's enough to make a cow move. Okay? You don't want to. The cow's being stubborn, don't want to move where you want it to. They put a cattle prod in there, stick them with a cattle prod. It's got 2 little electrodes on the end. It gives them a shock of electricity and makes them move along. Okay? And they'll kind of jump. All right? Well, think about it this way. Suppose we had a cattle prod, and we were to stick you with it. Okay? Right in the behind. All right? If I have the electricity or the level of voltage or the level of amperage really turned down kind of low, you wouldn't jump as high as if you got a higher volt, right? Higher jump in electricity, right? Higher amount, right? I mean, if you got stung more, you'd jump higher, would you not? Okay. Electrons are kind of like that. The more energy they have, the higher they exist in terms of how far they are away from the nucleus. Yep. Yeah, negative E is the symbol we use for an electron. Okay? All right. So then, electrons exist in these energy levels here. Okay, so this is the second energy level: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay? And so, as long as those electrons are in as low an energy condition as they can be, they'll exist in the lowest energy state, which means they're in the lowest energy ring, which is not really a ring, it's a circle, a sphere, which is not really a sphere, it's an energy level. Okay? It's a region of the periodic table defined by an equation that a guy named Schrodinger came up with. And if you're a fan of the Big Bang Theory, you know about what? Schrodinger's cat. Don't you know about Schrodinger's cat?
Yeah, we watched that.
There you go.
Yeah.
There you go, Schrodinger's cat. All right, hey, we'll get to that.
I don't really remember it.
You don't really remember it.
Watching it.
Shame on you. You should remember. You should remember. Okay, anyway. They do. You know what's funny? They deal with a lot of science in there. But what's the socially challenged physicist's name?
Raj.
What? Not Raj. He's not so much socially challenged. I guess he is.
Oh, to women.
Well, to women, that's true. Huh? Sheldon. He's the one that's really socially challenged in every respect. Okay? He has to write equations to figure out humor, right?
Yeah.
Okay. So, I mean, he's a genius, but, only when it comes to physics or something. Anyway, the point is that, well, I don't even know what I was getting to now.
Schrodinger's cat.
I know. I had to do something with Schrodinger's cat, but I forgot what I was going to tell you about. So I'll get back to it when I think of it. All right, back to here. All right. So, if we get to these energy levels here, this is representing the sublevels within that. So not only do we have primary energy levels represented by these concentric circles, which aren't circles, which are energy levels, okay? But within those energy levels, we also have electrons arranged in what are called sublevels, which are then arranged in orbitals. Okay, right now we're not going to talk about orbitals, we're only going to talk about these sublevels, okay? So this first section here, the first part of the representative elements over here, these first two columns, those represent what is called the S energy sublevel. Okay, S energy sublevel. But remember, I told you in the beginning that this stuff doesn't always work out nice and neat the way we'd like it to. Okay? In fact, helium, way over here, remember it's way over here on your periodic table right there? Okay? It actually belongs right here when we're talking about energy sublevels. Not when we're talking about other things, just energy sublevels. So what we want to do, can't seem to find the marker I want for that. What we're going to do is we're going to take and show helium only for S energy sublevels, only for sublevel regions, okay? We're going to move helium over there. And we're going to show that it belongs right here. Okay? Belongs right there. And so that's the S energy sublevel. I've been asked from time to time, what does S stand for, or these other letters I'm going to tell you. It actually is the first letter of a name, which defines the kind of bars of light you get when you do spectroscopy. We'll talk about that too. Okay? So basically, because electrons moving around in this energy level or moving around out of this energy level give you nice, clean, straight bars of light. Okay? So this one over here, this section in this area, in this part of the periodic table, this is the P sublevel region. And together, S and P give us all the elements that are in our representative elements, except that we had to move helium over to the left for our energy sublevels. Okay? So try not to confuse the two. The section in between here, these are called the inner transition elements, but for sublevels, we have a name for it, and this is the D energy sublevel region. And the last energy sublevel region is what nobody wants for a grade. Nobody really wants a D, but what do they really not want? An F sublevel. So this is the F energy sublevel region. Okay, so what are these things then? Let's see. See if we can write a definition that kind of, sort of, explains what we're talking about here. Okay? Okay, so energy sublevels or regions or areas or sublevel regions are areas of the periodic table in which we place electrons as we arrange them in orbital notation and electron configurations. That's about the best I can tell you what it means, okay? And we're going to learn about orbital notation and electron configuration in this unit. You're going to be able to write the orbital notation and electron configuration for all the elements in its upper part of the periodic table. We're not going to go to the F sublevel in this class. We're going to go to all these right here. Okay? Kind of looks like an E now, sort of, kind of. We'll dry out some more and I'll make it better. Okay? Now hold that thought kind of with you because we're going to come back to that idea. All right, we'll get back to that later and talk about it some more. Everybody finished with the notes on that? Okay. Now we're going to talk about some names that we give certain types of elements and where they're arranged on the periodic table. Okay? We have some special names for certain elements in certain columns of the periodic table. I think I've skipped over where I'm looking for. I mean, I can do it by memory, and I guess I will, but anyway. I was trying to keep them in order by what I had in the notes here, make sure I'm going to the right periodic table next. Okay, so except for hydrogen at the very top of this first column, let's look at the periodic table for a minute. Here's the first column of the periodic table, and there's hydrogen, okay? Except for that first element right there, all these elements in this column are called, this first column is alkali metals. I'm not kidding you. That's right. You know what the next column's called?
Alkaline.
It's close. Yeah, it's alkaline earth. Close to it, but you got to say both words. This is alkaline earth metals. Alkaline earth metals. No, I'm gonna go over here right now. Y'all know what those are called, right?
I remember seeing those.
These are all noble gases here.
Yeah, that's
Noble gases. Yep, that's right. Now he's got it. Okay. Noble gases.
Naval gases.
Noble gases.
Is that your final answer?
That's my final answer. This column next to the noble gases, these are, huh? I thought you knew.
I'm gonna say citric acid.
No. Citric acid is a compound.
Oh, okay.
Halogens. Halogens. All right. Alkali metals, alkaline earth metals, halogens, noble gases. Okay? Okay. You need to know that all the elements in this middle section here, we mentioned this a moment ago, they're called transition metals. Because they provide a transition between the representative elements. Okay, that's all it means. Okay? The representative elements are those that most clearly show the pattern of behavior that exists as we compare one set of atoms to another, their chemical behaviors. This is a transition area which kind of like sort of flattens out. It's like it doesn't really show a clear transition, but it's just moves you from here to there. That's all it does. Okay? Yep.
Did you mean for alkaline or alkali?
Alkali. This is alkaline earth. Okay, and because those words are really close together. I mean, in terms of spelling. So you have spelling counts here. Okay, you can't say alkali earth metals and expect me to give you credit for it. This is alkaline earth, and this is alkali. Okay, and a lot of people, you might have heard that term alkali. Sometimes it's used synonymously with what is meant by, in chemistry, a base. They're not quite the same thing, but most alkali compounds are bases. Not all of them. Okay, and they don't always behave that way, but that's why you get that sort of idea that they're the same thing. Yeah. Yeah. So this area down here in the bottom, these are called the inner transition metals. Is that a song that you actually heard? You just made it up just now.
I mean, I can make that a song.
Well, that's up to you. Sure.
Help me record it. So
Inner transition metals. Okay?
Those aren't the ones that have the highest, like the confidence, or whatever it is.
They won't have the highest atomic number, but they are among the highest. Okay? And let's look at that on the periodic table for a minute. Okay? Let me show you why they're called inner transition metals. All right? Everybody got the periodic table out?
I'm going to
All
write
right.
a song about periodic table.
Huh?
I'm going to write a song about the periodic table.
You are?
Yeah.
Good.
Hey, can we listen to that song that they have?
What song?
Oh, I love all those little corny
Periodic
songs.
table song? That's where they name all of
Which one?
the guy.
The Song of the Elements?
I was the guy that's
From
sitting
Harry
on
Potter.
that stool.
From Harry
The
Potter?
guy from Harry Potter did it, like on an interview. He's like,
Oh, yeah, but he got it because it was done by a guy from Harvard.
yeah.
Or no, he did it at Harvard. He wasn't from Harvard. I don't know. Anyway, all right. Take a look at these numbers down here in, this is row 1, 2, 3, 4, 5, 6. Now, let me go ahead and tell you this. Every row of the periodic table is called a period. Every row of the periodic table is called a period. It's a term you need to know. Every row of the periodic table is called a period. Every element in that period is part of period X. Okay, so hydrogen and helium are in period 1. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon are in period 2, and so forth. Does that make sense? So every row of the periodic table is a period. Every element in that row are part of that period. Okay? So let's go down here to 1, 2, 3, 4, 5, 6, period 6. Okay? If we were in a school that was not on the block system, we'd have 6 or 7 periods a day. We don't have 6 or 7 periods a day. Okay, we have only 4. All right. So take a look. Count the numbers. Count the atomic numbers. What happened? Are you looking? Are you following? Huh? Are you waiting on me to tell you? Huh? I don't hold your hand across the street. Look at this. What happened here?
You won't hold my hand across the street.
No, I'm not baby you here. I want you to do it for yourself. Figure it out. What happened here? It drops down. It's right down here. See, there's 58. And I'll go all the way through 71, and then you come up here to 72. Okay? So let me tell you how the periodic table probably ought to be constructed. We ought to cut it with a pair of scissors right here and spread them apart and stick that part up in there. But you know what would happen if we did that? It wouldn't fit on our sheet of paper. Okay? The only reason this is down here, the only reason that I know of this down here is because it won't fit on a sheet of paper like that. But you got to know that. Okay? You got to know this stuff down here fits right there. You should cut it right here in your mind. Can you see that in your mind?
Yes.
Can you imagine that? You got a good imagination? Can you imagine cutting that in two right there, spreading it apart and sticking this whole section right in there? Because that's really how it ought to be arranged. Got it? All right. That's why it's called inner transition metal. So these are simply special named regions Now, let's talk about these parts, these 1, 2, 3, 4 columns here that we haven't named. There are special names for those columns, but I'm not going to make you know those, okay? They don't come up very often. What we're going to do is, these are the noble gases right here in column number 18 or 7A. Okay, if you look at the top of our periodic table, it's got 18 here and 7A. I like 7A because it actually goes along with the way that the sublevels are arranged and the way we arrange the periodic table, what we do. So this is the noble gases. These are the halogens. This column right here is called the chalcogens, but I'm not going to expect you to know that one. This one, yes. Halogens, yes, but not chalcogens. All you got to do is say, this is the oxygen family. You with me? So what are we going to call this one, right? All the elements in this column? Nitrogen family. And we're going to call this one what? Carbon family. Okay, so every column of the periodic table is a family or group. You need to know those terms. All the elements in a column of the periodic table make up a family or group. Okay, write that down in your notes if you didn't already know that. All the elements in a column on the periodic table make up a family or group. So the noble gas family is over here. The halogen family is right here. The oxygen family is right here. Okay, nitrogen family, carbon family, and boron family. Okay? Got that?
Can you repeat that statement one time?
All the elements in a column of the periodic table, arranged in a column of the periodic table, make up a family or group. There you go. There you go. All right. Got that? All right, good.
Now where that line breaks is like carbon, just carbon and silicon, right?
Well, no. Carbon, silicon, germanium, tin, lead, those are all part of the same family. Okay? All right. Okay, you can flip your paper over. And we're going to talk about that stair-step line you were just asking about. You remember that one? What is that dividing line for?
It's like the gases.
No, not the gases. Okay. This stair-step line right here is the dividing line between metals and nonmetals. The stair-step line right here is the dividing line between metals and nonmetals. Okay? So here, 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 and here. There's our dividing line between metals and nonmetals. Oops, there's a problem.
What?
I said, oops, there's a problem. Remember our problem with energy sublevels? What was the problem? Helium needs to move over there. Okay, we're going to have to move something here too. Okay. So we're going to call these metals over here. And over here we're going to call all these non-metals. All right? Good. The problem is hydrogen. Okay? How many of you know what hydrogen is? How does it behave? What does it look like? What is it? What state of matter is it in? Huh? It's a gas. Yeah. Hydrogen in its elemental form is a gas, at least on our planet. Okay? And so metals, you ever see any metals that are gases? Not at normal temperatures and pressures. Metals are going to be solids, except for a couple of them. The only one you really need to know about is mercury. It's always a liquid. Okay? But hydrogen...
Isn't mercury in thermometers?
Mercury is in old thermometers. That's true. We don't put them in thermometers anymore, at least in the high school classroom or the high school lab, because mercury is so dangerous, insidious.
I broke the thermometer that had the mercury. mercury in it.
Where?
Like it kind of like it
No,
wasn't in my mouth.
Where were you when
in
you
my
broke it?
kitchen.
In your kitchen.
And like I was at the sink and I was trying to measure myself and then or temperature myself and like the thermometer came out of my mouth and it fell and I picked it up and then my mom was like, oh no, you're gonna die. And like,
Yeah, no, you won't die.
but then what happened? Like what happens then if you like touch it? Is anything gonna happen?
Well,
'Cause I touched
probably touching it a little bit wouldn't be a bad thing, but you don't want to leave it on your skin.
I washed my hands for like hours and cried.
Okay, well, it reacts with the salts on your skin, becomes an ion, and that's how it absorbs through your skin and gets into your liver and brain. Okay, so we want to try to avoid that. Okay, all right. So helium, I'm at helium. That's not helium. I know, it's just sad, isn't it? This is hydrogen. So hydrogen doesn't belong here. Okay, hydrogen belongs over next to helium. And we're talking about metals and nonmetals. Okay, it belongs right there. Okay, there's where hydrogen belongs. And we got a few more little things we want to put on here too. Okay, because this dividing line, while it would be nice if it were exactly that way, nature doesn't quite behave that way. Yeah.
I thought that hydrogen was in that little box and then we moved it over to that the other one.
No, helium previously moved over to the other side.
Oh, see, I put an H in.
For energy sublevels, helium belongs over here because it's in the S sublevel. Huh?
So they're just beside each other.
Yeah. So helium is part of the S sublevel region, but hydrogen is not a metal. Okay? So that kind of make up a special case here. So we got to. So when thinking about metals and nonmetals, you can't think of hydrogen as being a metal. However, that might not be the case near the rocky core of Jupiter. Are you listening? You don't find that interesting?
Yes, it is cool.
Oh, okay.
Rocky core of Jupiter, we got.
Yeah. So you know what Jupiter is, yes? Okay. What is Jupiter? It is a planet. It's a gas giant. It's the largest planet in our solar system.
Jupiter?
Yes, Jupiter. It is mostly made up of gases. However, the gravity on Jupiter is so huge that theoretically, people who are smarter than me think that hydrogen under that kind of pressure would behave like a metal. I don't know.
Until I go to Jupiter and find out.
That's right.
Is there not like land on Jupiter?
Well, you mean, there's a rocky core. There's a rocky center there around which all that gas flows. Okay? But yeah, you don't want to go to Jupiter because the gravity at the core is so huge. You wouldn't
But how
survive.
do you know? How do people know? Because they never knew.
Even in a suit, spacesuit,
Yeah, even in a spacesuit,
How do you know?
you'd be crushed.
where you burn because of the gas there.
Well, there's a hurricane essentially larger than the United States that's been there as long as they could see with a telescope the planet Jupiter.
What if it's not a hurricane?
Wait, what?
What if it's just clouds?
Yeah, that's right. As long as they've had telescopes to look at Jupiter, there's been this spot on Jupiter, and it basically is a hurricane. You read that?
And it rains like it's raining.
Oh, I don't know that it rains there. I don't know.
Exactly, so how do you know it's a hurricane?
Hold on.
Oh,
So it's a hurricane going on Jupiter right now.
Yeah.
but it's not raining, because you don't know if there's rain there.
Well,
That means there's water on Jupiter.
is there water on Jupiter? There is, yeah.
Or even like a hurricane of gas, something like that.
Yeah.
Okay, so like,
I think Jupiter's gas is mostly hydrogen and methane and things like that. It's not they don't have as much oxygen and water as we have. Okay? All right. Now, along this region here, because it really isn't a black and white issue, guys, okay? I mean, just look around the room. It's not black and white, is it? Because even the white people are not white, and the black people are not black, right? And we got brown people in between, all right? It's not black and white, okay? It's all kinds of shades in between, all right? Even me, if I go out and be out in the sun a lot, I get a different shade, okay? So, and that's what happens along here. They get a different shade along here depending on how you treat them. Okay? So elements that are right along this stair step, except for this one, aluminum is always a metal. But all the other elements that touch this stair step on two sides, okay, all the elements that touch that stair step on two sides except for aluminum, and including boron, because I say on two sides, you got to extend that line up there to know what I mean by two sides. Okay, those are all called the the metalloids. Okay, they're called the metalloids. So they're kind of like metals sometimes and kind of like non-metals sometimes. The reason that your computer works, or your iPad or iPod, all the electronics we have today work because of those areas near this boundary line here, near this boundary stair step that sometimes behave like metals and sometimes like non-metals. Okay? Because what we do is we get them to behave molecularly like electronics that we can see. We don't have to see them. They're so small we can't see them. We stick those little atoms in the middle of a structure of another set of atoms, and we get it to behave like little circuits. Okay, they switch on and off all the time, which is really cool. Okay, so the fact that I can record this video on my computer is due to that behavior along this region here. Okay, really cool stuff. Before that, we had to have vacuum tubes to do the same work, and so a computer that would do well. We didn't have computers that would do the work my cell phone would do, okay, or your cell phone will do. This has more computing power than any computer that was around before we had solid-state electronics. Okay, the first computer filled up a room that was, I'm guessing, about 8 times the size of this room, and wouldn't do as much as your calculator will do now. Okay, the computer on board the spaceship that landed on the moon. The computer on board the spaceship that landed on the moon was not as powerful, anywhere near as powerful as your cell phone is. Was not anywhere near as powerful as most of your calculators. Okay, I mean, they just didn't have it. It wasn't around. Okay, so electronics have come a long, long way in a very short period of time. All right, now let's talk about some other, that's kind of like laying out the regions. Let's talk about what we can use some of that for. I want to talk about atomic size for a minute. Because atomic size is really kind of cool. Let's call this, when we get as a title, metals and nonmetals, okay? All right. So by knowing where the elements are arranged on the periodic table, we can figure out a lot of things about behavior already. We can know whether they behave like metals or nonmetals. Yeah.
Are we going to have to know all these parts?
Yes.
Okay.
You have to know all these things. Okay. So let's talk about atomic size. Atomic size. So let's go back to your periodic table here. And let's see. If we looked at hydrogen, which is right here, and go across that first period to helium, which one is larger? Helium has an atomic number of 2, an atomic mass of 4, roughly. Hydrogen has an atomic number of 1, an atomic mass of 1. Which one's larger?
Atomic size?
Hydrogen's larger. Who said that? How'd you know that?
What?
Because you figured it was a tricky question I was dealing with? A physical science teacher taught. Well, good for your physical science teacher. I'm so proud of them. Okay. Let's look at the next row here, lithium and beryllium. Okay, lithium is atomic number 3, atomic mass of about 7. Beryllium is atomic number 4, and atomic mass of 9. Boron is atomic number 5, and atomic mass of about 11. Okay, would you think that boron is smaller or bigger than lithium? Smaller. Huh? Really doesn't have so much to do with metal as it has to do with what's called what we call the shielding effect. And I'm going to explain that in a minute, okay? All right. What you need to know in terms of a pattern, though, is that as we go across the periodic table this way, the element sizes get smaller. the atom sizes get smaller. As we go across the periodic table this way, atom sizes get smaller. Now, when we go down in any row, they get bigger. Yeah. Okay? If we go across the row, they get smaller. If you go down in the column, they get bigger. Okay? So they get smaller going this way. And they get bigger going this way. So based on that, we're the largest elements. Bottom left. Okay? Bottom left, we're the largest ones. So if we look at the smallest ones and go into the largest ones, we go like that. Okay, so the largest ones are down here. The smallest are up here. Yeah, you wouldn't want to hold that in your hand. You're right. The question was, isn't radium dangerous? Yeah, you don't want to hold that in your hand. Radium was used to paint the numbers on watches during World War I because soldiers in the trenches in Europe, where they were fighting World War I, need to be able to see their timepieces at night. I said watches. They're pocket watches, not watches like fit on your wrist. Okay? Pocket watches. Yes. You know what a pocket watch is? Okay. Yes.
Wasn't the lady that discovered more than radium damage?
Let's see. You're talking about. See, I'm just having trouble today. I know her. I can see the picture of her right now. Pierre and Marie Curie. Okay. Yeah. She died of radiation poisoning, basically. Okay. She discovered radium and polonium. I'm sorry, polonium was named for her. I'm not sure if she discovered it or not. Maybe so. Seems to me she did. Don't hold me to that. Look it up, okay? But she was the foremost authority on radioactivity in her day. Now, her husband died before she did, okay? And she carried on the same work they were both doing, but she never got the recognition that he did in her lifetime. Because back then, women weren't considered to be very smart, okay? No, don't say that. Don't say that. So we know that's not the truth anymore, okay? Right now, more girls go to college than guys do. There you go. All right, just so you know. All right. I mean, there was a time when, by and large, people didn't think certain people of certain races were as smart as other people of other races. Okay, we know that's not true. Huh? Either smart or you're dumb? Okay. You know, what is it that that guy on the movies said, in the book said, stupid is as stupid does? Yeah. Huh? Forrest Gump. Yeah. Stupid is as stupid does. Yeah. Stupidity isn't so much, how much you know or can do. It has to do with what you do. Okay? Or not what you can do, what you do. I like the quote I have up on the wall by Einstein. And you read that the other day for us, didn't you? Yeah? Okay. Everybody's a genius. Everybody's a genius. Everybody's smart about some things. Certain things everybody's really smart about. But if you judge a fish by its ability to climb a tree, it's just not equipped for that, right? If you judge a fish by its ability to climb a tree, it will live its whole life believing that it is stupid. So if you ask everybody to do the same thing, some people are going to appear smarter than others. Turns out that everybody's smart about something, smarter than me about something, smarter than you about something. Okay? But it has to do with the way your brain is wired and what your abilities are. Okay? The only thing we measure in school is your ability to process numbers and write sentences and those kind of things. Okay? We don't really judge in terms of grades the other things because that's what we decided we're going to measure in school. All right? Doesn't mean you're not smart. Just means that that's what we measure in school. Okay? All right. So in terms of atomic size, the reason this behavior occurs is because of something called the shielding effect. And let's talk about the shielding effect. Okay, we're going to go back to our drawing of those concentric circles, which aren't really circles. They're more spheres, which aren't really spheres. They're really energy levels. Okay, remember this stuff? Remember this? Okay, all right, let's talk about it. I'm going to draw a new drawing of it down here because I want to kind of illustrate a point where I need some more space, and I want to get rid of some of those little electron bumps on there. So here's our first energy level. Okay, now what are electrons made of? Electrons are little energy packets. Okay, and what makes the lights in our room work? Energy. What kind of energy? The electrons. Electrons moving along in a wire and in the bulb, okay, that is what makes that light work. So this is energy, okay? And as those electrons move along there, they actually create an energy field around them. Electrons moving in this direction create an energy field around that pathway, okay? That's why the radio in your car works, or your TV at home. Well, it used to be because of how your TV works. Now we got everybody got cable and satellite. But it used to be, if you still have a TV with an antenna, you get a signal from a station over the airwaves. Okay, this is the way your cell phone works. Let's use that example. Okay, because electrons flow in a certain direction, they generate an energy field around that. That energy field is transmitted, called radio waves, electromagnetic radiation, to an antenna buried in the circuitry of your cell phone, and it's turned back into electrons moving around. Okay, that's the way your cell phone works. Okay, so these electrons moving around in here create an energy field. All right. So you've ever, how many of you know enough about science fiction to know what a force field is? Okay, you know what a force field is? Yeah. What does a force field do?
Can't get through.
Yeah, can't get through it. You know, the spaceships in Star Wars don't get blown up every time they get hit. Well, Star Wars is a little bit different, but Star Trek, okay, they have these force fields, okay? Well, there's kind of a force field here, okay, because these electrons are moving around in this region. So when I add another level of electrons, okay, our second level of electrons here, the neutrons, or the protons rather, in the nucleus, which are holding on to those electrons, okay, they can't hold on to these electrons quite as tightly as they hold on to these because they're having to penetrate through this force field. Does that make sense? That's the shielding effect. All right? So every time we put one, let's say we put 2 electrons here, we put 1 here. It's very hard for the 3 protons of the nucleus to hold on to that 1 electron. It starts to flop around out here, makes that size of the atom bigger. Does that make sense? But if I have 6 electrons in the nucleus, and that puts 4 electrons in this second level, well, there's more protons in here and more electrons, so there's more pull, and it shrinks down the size of that sphere, that electron field, that electron energy level. Does that make sense? And so, as we add more protons to the nucleus and add more electrons to that energy level, ooh, I made a mess here. What's that? All right, then the size of that energy level made up by those electrons gets shrunk down. Does that make sense? That's called the shielding effect. Are you with me on that? Because that's important. You need to know what the shielding effect does. Okay? Can you take a moment now and write a short paragraph on what the shielding effect is and does? All right. Electrons, when they move around, create an energy field around them. Okay? So electrons in this first energy level create an energy field in this region. The protons in the center have to pull on the electrons in the next level through that energy field, a kind of force field. Not a complete force field that prevents anything from getting through there, but a partial force field in the sense that we think about it in science fiction. Okay? And so if I put 2 electrons here, 2 protons in the center, 2 electrons in this first energy level, Then I put a third proton in the center, and the third electron goes to this next energy level. Those protons now have to penetrate through that kind of force field to get to that electron. And so it's not held as tightly. It's kind of flopping around out there, and it's held, but it's not held as tightly, so the size of this cloud spreads out. So the size of this atom is going to be kind of big compared to what happens next. If I put another proton in the center and another electron out in this energy level, there's more force to penetrate through the force field to pull on the electrons. There's more electrons to be pulled on. They're held more tightly, and the size of the electron cloud shrinks. Put another proton in the center and electron out here. So now we got 5 electrons and 5 protons. Okay? So there's more protons, and there's 3 electrons in this outer energy level because 2 of them exist in this first level. You can shrink down that cloud of electrons a little more. And by the way, we call that an electron cloud because it's not an actual shell. It's not an actual circle. It's a cloud, like the cloud in the sky. In the sense that you don't always know, not every electron is in a place we can find it every time. Okay, that's called the Heisenberg uncertainty principle. Okay? You shrink it down until we fill up that level. Remember we said we can only put 8 electrons in that second level. Okay? So once we get to 8 out here, we've got to go to another level, and the thing starts all over again. 1 electron in the outer level, hard to pull on it, it gets bigger. Okay? And so we add more protons in the center, more electrons to that next energy level, we shrink it down and shrink it down and shrink it down. Does that make sense? All right, I want you to take a moment and in a paragraph, in your own words, describe the shielding effect. Now, I know in physical science you learned about ionic bonding versus covalent bonding. Yep. All right. You learned it on 21 Jump Street?
Yeah.
Oh. Have you ever seen,
Uh-huh.
there's a cable channel, Ion Television?
Oh, yeah.
You ever seen their commercials? What do they say on their commercials?
I don't know.
Ion Television, positively entertaining. It's a chemistry joke because ions are positively charged or negatively charged. Okay? You didn't know that? See? Your life is just enriched by the stuff you know. All right. You don't get the joke unless you know. All right. Shh. Let's talk about forming ions. Now, there are different kinds of ions. There are monoatomic ions, and there are polyatomic ions. So let's see, monoatomic. What do you think that means? One what? One atom. Okay? So a monoatomic ion is an atom that is charged either positively or negatively. Now, how would we get an atom to be charged positively? Let's think about the structure of the atom. You got as many protons as electrons, yes? You got protons which are positively charged and electrons which are negatively charged. Those two charges, positive and negative, cancel each other out. So an atom that has an equal number of protons and electrons has no overall charge. So how would you get a positive charge? More protons. You just remove an electron or more than one electron. Okay? So, atoms that are positively charged, ions, monoatomic ions that are positively charged have lost 1 or more electrons. Good definition to remember. Okay? Monoatomic ions that are positively charged have lost 1 or more electrons. If they've lost 1 electron, that's a 1 plus charge. Ions, which are positively charged, monoatomic ions, which are positively charged, have lost 1 or more electrons. Okay? Ions, monoatomic ions, which are positively charged, have lost 1 or more electrons. Okay? Now you have to remember, when I say lost electrons, we're talking about from the atom. Okay? If you need to write that down to remember that, write that down too. So they've lost 1 or more electrons from the uncharged atom. Okay? Now if you have a 1 plus charge, it means you've lost 1 electron. If you have a 2 plus charge, it means you've lost 2 electrons because you have 2 more protons than electrons. If you have a 3 plus charge, you've lost 3 electrons.
Yeah.
Now, what about negatively charged monoatomic ions?
Lose protons.
They gain electrons. You don't lose protons because the protons are in the nucleus. You don't lose those. That's kind of hard to do. Okay? It's a lot easier to get rid of those electrons, which are on the outside. They're smaller, easier to get rid of. Okay? So negatively charged ions have gained 1 or more electrons. Gain 1 electron, what charge do you have? 1 negative. Gain 2 electrons, what charge do you have? 2 negative, and so forth. Okay? Does that make sense?
So the negatively charged monoatomic ions is what?
Negatively charged monoatomic ions have gained 1 or more electrons. Gain 1 electron, it's 1 negative. Gain 2 electrons, it's 2 negative, and so forth, and so on. Okay? Now, here's what happens. The atoms in this column right here, what we called a while ago the halogens, they tend to lose only 1 electron. The elements that are in this column of the periodic table right here, in simple, what's called binary compounds, they tend to lose only 1 electron. Okay? So what charge are they most often going to have? They gain 1 electron. I'm sorry, did I say gain? Did I say gain? Gain 1 electron. So they're going to have a 1 negative charge. Okay? Let's take a look at the periodic table on the next page.
Well, I think so they lose.
I'm sorry. Elements in this column of the periodic table, what we call the halogens, tend to gain 1 electron. Okay? So they tend to have a 1 negative charge. Let's look at this periodic table right here with the oxidation numbers. Do you see 1 negatives on this column right here? They're the ones in the boxes because that is, now these are common oxidation numbers. So like chlorine has 7 common oxidation numbers. But the most common of the common charges is a 1 negative. In a binary compound, that is 2 elements bonded together, these elements right here are going to have a 1 negative charge every time. Okay? In this column, they tend to lose gain 2 electrons, so they gain a 2 negative charge. Okay? Look at the common oxidation numbers here. Do you see anything in common in here? Well, I see a 2 negative in common in all these. There is a 6 plus in there sometimes, but there's that 2 negative everywhere. That makes sense, except for polonium. Okay? Alright, so 2 negative is the most common oxidation number here. Alright, do you see a pattern in the next one at all? I see 3 negative in all those except for bismuth down here. Okay? So, 1 negative, 2 negative, 3 negative. There's a nice pattern, isn't there? When we arrange the elements in the periodic table, we get patterns. Does that make sense? Alright? How about over here? What do you see? See any patterns in these columns? 1 positive except for hydrogen, which kind of goes back and forth between being non-metal and metal, kind of. Okay? 1 positive, 2 positive, 3 positive, and then they start to kind of get kind of funky in here. But you need to know the elements in column 1 tend to be a 1 positive charge. Elements in column 2 tend to be a 2 positive charge. When they have become an ion, in this column right here, which is called 3b, there's Roman numeral 3b, we get a 3 positive charge. Now, after that, these kind of get funky until we get over here in this column. These in this column, which is 2b, 2b or not to be? That's the question. Okay. They tend to have a 2 plus charge. You got to know that. Okay? This column here tends to be what charge? There's a pattern of 3 plus, and that's a 3a. So these Roman numerals at the top kind of help you figure that out. Roman numeral 1, 1 plus. Roman numeral 2a, 2 plus. Roman numeral 3b, 3 plus. Roman numeral 2b, 2 plus. Roman numeral 3a, 3 plus. Of course, they don't quite fit over here when this is 7a, but that's 1 less than 8. Okay? And 8 is the octet. 8 is the perfect number. Okay? I don't know, in my Sunday school class we say 7 is a perfect number, but in chemistry, 8 is a perfect number. Got it? All right. So let's talk about how that affects ionic size. Okay? Right along here somewhere, and it's not a perfect line, okay? I kind of did a squiggly line because it's not perfect. Alright? But I'm not going to ask you to know the ends, all the little details here, but in general, here's what I want you to know. Ions in this column, ions, that means in this column they're losing one electron. Ions in this column tend to be smaller than the corresponding atom. Ions in this column tend to be smaller than the corresponding atom, and as you go across each row, they tend to get even smaller, just like the atoms, until we get to there. Okay? So they start out smaller. Okay, they start smaller. They keep getting smaller until we get to there. Smaller in that direction. Okay, right along there, this is where they start to gain electrons. So they're losing electrons, they're getting smaller by the shielding effect, okay, and by virtue of the fact they're losing more electrons, we go to the right. Then we get over here, we start to gain electrons instead of losing them. So they get huge right along here. They just swell up, huge, okay? And they get smaller again. Okay? And then we still get bigger going down. Alright? So that's the pattern for ionic size. I'm not sure why you even need to know that, but it's in the state standard, so I teach it to you. Okay? It doesn't really come up much after this unit anyway, but it's something we need to know.